Back to my YouTube channel once more. We're still under engineering science and form. We're dealing with stress and strain. We have given question 6, right? Says typical question that we have given there. We have given 6.1. State the Hooke's law. States the Hooke's law. 2 marks there. We want to state that 6.1. We should state the Hooke's law. Hooke's law states that Hooke's law states that within 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 the elastic limits within the elastic limits of any body, the ratio of stress to strain, right, produced is constant. We know that within this, guys, the limiting of proportion within this body, the ratio there, it's constant. Hooke's stress states that the elastic limits of any body, the ratio of stress to the strain produced is constant. States that within the elastic limit, within the elastic limit. So yeah, this is how we can define these, guys. All right, so I've given 6.2. Let me just cancel this. Let's go to the real deal now. Let's go to the real deal. So 6.2, in the figure below, the mid-steel bar width, which is axially loaded by means of tensile loads, so that the maximum induced stress we have given is 120 megapascal. Young modulus of elasticity is 210, guidance 200 gigapascal. You see, if you can check here, this is a force that will take place throughout in all of that. The Young modulus is for all these bars, guys. Those bars are placed in series. We have bar 1, we have section 2, or what we call, so we have section 2 there. As you can see here, we have section 3. So they have diameters. We have the length of that section, we have the length of the second section, we have the length of the last section part then. So we've given that the force that is applied there is 100, and we are not given. All right, we are not given, sorry, that is megapascal. It's a stress. Okay, we can get that force there. We don't know that force. We're given the stress. We've given that stress. The stress is the same that is acting on this thing there. Says calculate the total change in length. We don't know this, guys. Right, so what now, guys, we want the that force there. Supposed to get that force, isn't it? We have to get that force there. All right, so I don't know, but force is equal, okay, stress is equals to force over area. But as you can see, guys, is applied here on this portion. So that diameter there is what is 30. So we have to find out the force there. You can multiply that side. Then the force will be equals to stress multiplied by area. Then we have stress is 120 megapascal. 120 times 10 to the power of 6. Area is pi over 4. The diameter is acting where? At this section, guys, as you have seen, that diameter there, it's what is 30. So we have 0, 0.03 squared. So what will be the force if I punch this there? 120 times 10 to the power of 6 multiplied by pi over 4 into 0.03 squared. This is 84,82823. What is that? Kilonewtons. Will be kilonewton. Alright, this is what we have. We have now that force. We have now this force there. Alright. The force will be the same throughout, by the way. So what we have now, we should calculate the total change in length. The aim is to calculate the total change in length. So the total change in length, we can typically, if we can say the total change in length will be the change in length for first portion, change in length for second portion, change in length for third portion. So we know that the change in length is force multiplied by length 1 there. The area of the second portion of the first portion multiplied by Young modulus is the same, plus x. What I'm doing is no x, guys, sorry. Multiplied by force multiplied by the length 2 of the second portion, area 2 Young modulus, plus force multiplied by L3 over area 3 multiplied by E. Why I did not wrote this E3, I leave it like that, is because these guys is the same. They gave us they gave us one tensile there. As you can see, we have Young modulus of elasticity. So, and then the force will be the same. If I can factor out the total extension, let me factor out these guys, is the same throughout. I would have F over E. It will be L1 over area 1 plus L2 over area 2 plus L3 over area 3. So if you have this now, guys, you can do your things. What is the force? Is the one we've just calculated it, which is 48,823 times 10 to the power of 3 divided by Young modulus. Young modulus of this is 200, as you can see there. So 200 gigapascal. This will be 200 times 10 to the power of 9. All this into what? The length 1. What is the length of the first portion? Can check here. We have the length is 200 millimeter. the diameter is 50. 200 millimeter, the diameter is 50. We have there 200 millimeter is the same as 0.2 in meter, right? Divide by pi, or let me just multiply by 4 here. It's a one and the same thing. Remember, if you have a fraction like this, 1 over, let's say, b over c, you can rewrite this. You can take this to the top. It's the same as c over b. So I did this. I took that 4 there on the top, so that you'll understand it. Similarly, if you have one example, let's say you have b over pi over 4 d squared. You can take this 4 there on the top. It can be 4b over pi d squared. You can write like that. It's a matter of maths. Is 19 wrong there. Multiply that by 4. Then the diameter there was 50, which will be 0.05 squared, plus the length of the second portion and the area. Let's check. We have 40. The diameter, this is 175. The length is 175, whereby this is same as 0.175 divided by, multiply by 4 also, divide this by pi over 0.04 squared. Alright, plus now the length of that section. We have the diameter is 30, the length is 150. So the length is 150. It's the same as 0.15 divided by, multiply by 4, divide this by pi into 0.03 squared. All this. Now I punch this. Remember, now if I punch all of this, I will get the total extension. By the way, total extension. Therefore, if we punch that, we'll get our total extension to be equals to what? All right. I have 84.823 times 10 to the power of what? Of 3. 200 times 10 to the power of what? Of 9. Okay. Multiply this into what? 0.2 times 4 into pi, multiply by 0.05 squared plus 0.0175 times 4 over pi into 0.04 squared plus 0.15 times 4. Divide this for pi, multiply this by 0.003. okay, the space, guys, let me just take this step by step. Imagine the time I've just have consumed the space. Okay, nevertheless, let me just simplify this, guys. The inside, let me punch this because the calculator there, the space there, let me just punch this. Okay, if we punch that only, I'll have 0.4 0.2 times 4 into pi into 0.05 squared plus 0.75 times 4 into pi into 0.04 squared plus 0.15 times 4 into pi 0.03 raised to the power of 2, like this. This is what we have, x equal, this will simply equals to, okay, to this, then I multiply this same time by, on the calculator, 84,823 times 10 to the power of 3 divided by 200 multiplied by 10 to the power of 9. This will be what? All of this will be 192,262. Okay, times 10 to the power of minus 6. This is what it's in meter. That is our total extension. Right. The total change in length is that, guys. That is what we have, the total change in length. All right. So this is what we have in this typical question. This is what we have so far. And by the way, let me just take some, I have some, let me grab this equation here, wait a little bit from the photos. Yeah, I have this. Let us deal with this one again. Because it contains, it's a continuation here. I forgot to put this one, supposed to contain here. Remember, if you can check, this it was 6.2, supposed to contain to 6.3. So we have this 6.3 here, so must supposed to become a continuation. 6.3 if given, say during a tensile test on a round bar of 25 millimeter diameter and the load of 80 kilonewton causes an extension of 0.2 millimeter. The initial length was 250. Calculate 3 or 6.3.1. The stress, we know the stress is equals to force divided by area. What is the force? It's 80 times 10 to the power of 3 divided by area will be pi multiplied by 4. Diameter there will be 0.025 squared. Then this what will be the answer there? 80 times 10 to the power of 3 multiplied by 4 pi into 0.025 squared. This will be 162,975 megapascal. This is what we have now. We'll have now 6.332. The strain, remember the strain is equal to the change in length over the original length. The change in length is 0.2 millimeter, as you have seen there, divided by original length is 250. Initial length was 250 millimeter. These millimeters and millimeters will cancel, then this will be equals to what? 0.2 divided by 250 simply equals to 800 times 10 to the power of minus 6. Remember, it has no SI units. This strain has no SI units, will be like that. So what we have here, 6.3.3 Young modulus. Young modulus is the stress over strain. Young modulus is calculated, it's the same as stress over strain. There are many formulas. Some can say Young modulus, it's a force multiplied by length divided by area multiplied by, okay, that is a change in length multiplied by Young modulus, and make Young modulus the subject of the formula. This will be equals to yeah, you can use this formula, guys. Sorry about that notification. Without wasting time, you can make Young modulus of elasticity the subject. It's F multiplied by length over change in length multiplied by L. It's either you use this or you use this. I will use this, guys. The fastest one. Ooh, okay. Also, this is good. Remember the force, we did not calculate the force. We're given the force, we're given the length, we're given the extension, we've given the area. Or yeah, this is safe because everything was there. It's a safe one. Here, if you remember, if might happen that your strain is wrong, you are at mess. So Young modulus, you can start by using that. You'll see the shear stress is the one in the same, is the one that we have calculated. The stress is that divided by shear strain. So okay, let me start by calculating using this formula, then we'll come and use this one. We have 162, the stress there, 975 times 10 to the power of 6 divided by Young modulus, which you divide by strain, minus 6. So let us check here. Young modulus 162,975 times 10 to the power of 6 divided by 800 times 10 to the power of minus 6. Okay, this will be 023,719 gigapascal. So let us check this one, guys, that formula, which that states that, where is that formula that says X will be force multiplied by length over the one of Young modulus. Young modulus again is given by force multiplied by length, change extension multiplied by the area. Let us check this one again. The force we have given in the beginning there, it was 80 kilonewton. The length initially it was 250, which is same as 0.25 divided by the extension. Here was the extension of 0.2 millimeter. This is the same as 0.2 times 10 to the power of minus 3 multiplied by the area. The area would be pi. Let me multiply by 4 there. Then the diameter, it was 25, which is same as 0.025 squared. Let's check. Someone can calculate in this manner. Times 0.25, so 0.2 times 10 to the power of minus 3 times pi times 0.025 squared. One here will have here I got 023,718 gigapascal. Let's check what do we have. You see the difference is slightly, you see that one is 0.9 here due to rounding off, but because here everything was given, this is the most accurate because we've given this from originally. There's nothing we've calculated, this we given, so this one is a most accurate one. So okay guys, this is what it is. So thank you for watching. All right, may you kindly, guys, you can become the part of the family. Become the part of the family by subscribing to my YouTube channel. As you subscribe to my YouTube channel, I'll be keeping on posting some nice content for you. I'll post some nice content. I will dish up for you some nice thing. So become the part of the family by supporting me, by subscribing. Then you are the part of the family. Feel free to like and comment, and feel free to share this to your fellow classmates. All the best.